So today we are going to discuss the next module, that is mechanical properties of metals. In this topic we'll discuss the overview of mechanical properties of metals, that is introduction part, and in this session we will discuss tension test or tensile test, which is one of the mechanical test in order to mechanical test which is carried out in order to determine certain mechanical properties, that is tensile properties. Then we will discuss the behavior of sample during tensile testing, then fracture, and finally the summary. The mechanical behavior of material reflects the relationship between its response or deformation to an applied load or force. The key mechanical design properties are stiffness, tensile strength, yield strength, hardness, ductility, and toughness. The mechanical properties of materials are determined by performing carefully designed laboratory experiments that replicate as nearly as possible the same service conditions. So factors to be considered include the nature of the applied load and its duration, as well as the environment conditions. The environment conditions are very important in mechanical properties because some of the materials shows different mechanical properties as the temperature or environment condition changes. The role of structural engineers in this mechanical testing field is to determine stresses and stress distributions within members that are subjected to well-defined loads. This may be accomplished by experimental testing techniques or theoretical testing by simulations. The role of materials and metallurgical engineers, on the other hand, are concerned with producing and fabricating materials to meet service requirements as predicted by the stress analyzers. So this necessity involves an understanding of the relationship between microstructure of materials and their mechanical properties. One of the most common mechanical stress strain test is tensile test. So this tensile test can be carried out by using different various testing standards. The popular standards in India is IS 1608, in ASTM standards ASTM E8, and as per ISO 6892-1. So these are the generally popular standards which are used for tensile testing. As you can see in this particular figure, the sample is loaded in the tensile testing machine. This is the schematic of tensile testing machine. Generally, universal testing machine or electromechanical tensile testing machine are used in order to carry out tensile test. A specimen is deformed usually to fracture with a gradually increasing tensile load that is applied uniaxially along the long axis of a sample. So this is a schematic of tensile testing machine. You can see it here. So these are the number of different tensile test samples prepared by using various standards. As the standard changes, so these values of gauge diameter, so this diameter or the width values and the radius values changes. So you can see one of the model of tensile sample is loaded in this machine, and these two marks indicates the gauge length. So the gauge length is nothing but the length which is under observation. So this gauge length can be used to find out the percentage ductility, that is percentage elongation, and that is nothing but change in length divided by original length into 100. So you can measure the diameter of the sample initially before loading. So that is that diameter we call as a gauge diameter, and this gauge diameter is very important in calculation of original cross section area of the sample. As we know, stress is nothing but load divided by area. So area calculation can be carried out by knowing the diameter of the sample. So what happens when loading starts? This movable cross head moves on the upside and this is a stationary cross head. So the sample at one particular state starts yielding plastic deformation of the sample starts. Initially it shows elastic deformation, and after one point it shows plastic deformation. And at one particular point sample breaks into two pieces. So again, after breaking the samples, join the two samples together and find out this distance between these two marks. Obviously, after fracture, the distance between these two marks has been increased in some percentage. So that we call as a final gauge length. Similarly, find out the diameter of the sample at the breaking point or at the break region, and that diameter we call neck diameter. Remember the term gauge length, final gauge length, original diameter and the neck diameter. So by using final gauge length we can find out percentage elongation, that is percentage elongation equals to change in length divided by original length into 100. Similarly, percentage reduction in area, final area divided by original area of the sample into 100, you will get percentage reduction in area. So the result of tensile test is nothing but you will get nowadays all the machines are computerized, so you will get the two columns, generally two column data, that is load versus deformation. By using this load versus deformation you can plot load versus deformation curve or convert the load values into stress and deformation value into strain and find out stress versus strain curve. So nowadays all the machines are computerized, so you will get automatic stress versus strain curve, or you can plot manually also. Tensile properties. So most structures are designed to ensure that only elastic deformation will result when stress is applied. A structural component that has plastically deformed or experienced a permanent change in shape may not be capable of functioning as intended. It is therefore desirable to know the stress level at which plastic deformation begins or yielding occurs. So for metals that experience this gradually elastic plastic deformation transition, the point of yielding may be determined as the initial departure from linearity to non-linearity. Very simple to understand. So as you can see it here, so this is a stress versus strain, part of stress versus strain. So this part is a linear up to this point, and after that it becomes non-linear or curve starts, means it is indication that from this point onwards yielding or plastic deformation has started. Meaning is very simple, up to point P the proportional limit exists, means Hooke's law obeys. Beyond point P and the Hooke's law is not obeying, and from this point, ideally speaking, to be very honest with you, there is no difference between point P and the yield point. Both are practically same. But from this point onwards, yielding starts. Means plastic deformation starts. And this point can be very easily identified, the point from which the non-linear portion starts. There are certain steels where you can see this kind of behavior, where two yield points exist, upper yield point and lower yield point. So this upper yield point and lower yield point can be easily identified by using stress versus strain curve. But in the previous figure you can see there is no upper yield point and lower yield point. So how to determine yield stress in this particular case? One thing you can directly go for the point where non-linearity starts. If it is very difficult to find out that point, then go for offset yield point method. So what is that offset yield point method? So generally find out the strain or the point, strain point where strain is 0.2 percentage, and from 0.2 percentage strain draw a line parallel to the linear line. So you can see, so this draw a line parallel to the linear line and it will cut at this point somewhere here. So means this point, the stress corresponding to this point we call sigma y 0.2. We will write sigma y 0.2 means it is a yield strength corresponding to 0.2% strain, and this yield strength can be used for design calculations. But in this figure you can see there is a two yield points clearly identifiable. So in that case no need to go for offset yield point method. So directly you can find out upper yield point and lower yield point. And this phenomena where you can see upper yield point, lower yield point, then some heterogeneous behavior here. So this phenomena we call yield point phenomena. So what is this yield point phenomena? So we'll try to understand this yield point phenomena for simple plain carbon steel sample. Suppose simple plain carbon steel sample is loaded in tensile testing machine and loading starts. So as the loading starts, as we know, in case of plain carbon steel, so carbon atoms are present, and obviously the size of the carbon atom is less than 1 angstrom. So you will get an interstitial type solid solution in case of steel. So this is a carbon interstitial atom and this is the dislocation. So the best position for carbon is below dislocation line. So you can see the carbon atoms are present below dislocation line because this is a low energy area for carbon atom. And when loading starts, you can see when loading starts, so this is a elastic deformation, means there is no steel dislocation movement. There is no dislocation movement in this particular region. Why? Because dislocations are not moving since carbon atoms are anchoring the dislocations. So stress is continuously increasing. You can see the stress is continuously increasing, still no dislocation movement, no plastic deformation, because of the carbon atoms they are anchoring the dislocations. And at one point, so that's why you can see there is a sharp line or sharp point exists here, and it's a linear region. Stress is directly proportional to strain, and at one point what happens, loading increases in such a level that so dislocations now turns away from this particular carbon atmosphere or carbon interstitial atoms. As we know, stress required for dislocation movement is very low. So suddenly, so this load value, load region or load curve drops. So the reason for load dropping is now the dislocations are not in contact with the carbon interstitial atoms. So this atmosphere of carbon interstitial and dislocation we call quadrille atmosphere. And due to this quadrille atmosphere you will get sharp upper yield point. And when dislocations are torn away from this carbon interstitial atmosphere or carbon interstitial atoms, suddenly this stress drops, because we know that stress required for dislocation movement is negligible, and that's why there is a sharp reduction in the load value or stress value. Now from this point you can see, as we know, stress required for dislocation movement is almost negligible. So at constant stress or at constant load, dislocation movement starts. But this particular region is not homogeneous, it's a heterogeneous behavior. The reason for this heterogeneous behavior is explained here. As you can see it here, exactly at the lower yield point, over the tensile samples, some bands are forming just exactly 45 degree to the tensile axis, and these bands we call Luther's band, and this Luther's band exactly 45 degree to the tensile axis, and this each jog corresponding to formation of new Luther's band. And at constant stress, so these Luther bands are propagating over entire sample, and at this particular point again stress value increases because all the Luther's band has now completely covered the tensile sample. So these Luther's bands you can see over the tensile sample by using your naked eyes also. Some slip lines, or we call some ring lines, are forming over the sample, and those lines are nothing but the Luther's band. And from this point onwards again stress value is increasing. You can see here again stress value is increasing. It is due to strain hardening. Already we have discussed strain hardening mechanism, strain hardening strengthening mechanism, where During plastic deformation, multiplication of the dislocation occurs, and each dislocation acts as an obstacle for another dislocation, and from this point onwards strain hardening phenomena comes into play, and that's why load value or stress value is increasing, means more stress or more load has to apply for further plastic deformation. So this phenomena we call as a yield point phenomena. So behavior of sample during testing. So as we discussed in previous slide, so after strain hardening, you can see, so after strain hardening, so from this point strain hardening starts and it continues up to point M. So point M is nothing but maximum load observed in this particular testing. So that is the maximum load. So load corresponds to peak load, and from this maximum load you can see again load value is decreasing. Now it is due to necking, you can see it here. So after point M, or after when stress strain curve reaches high stress, or load versus elongation curve reaches high load, maximum load, peak load, and after that peak load you can see the necking of the sample starts, means cross section area of the sample is now continuously decreasing. So that's why the stress value is also decreases, and at point F fracture occurs, means sample breaks into two pieces. So you can find out the tensile strength, that is load corresponding to point M divided by original cross section area, you will get ultimate tensile strength of the material. Similarly, you can find out 0.2% yield strength, that is load corresponding to 0.2% yield divided by original cross section area. So this is a schematic representation of tensile stress strain behavior of brittle and ductile metals loaded to fracture. You can see, so this is a ductile material and this is a brittle material, means in case of brittle there is no plastic deformation at all, just close to yield point sample breaks into two pieces. But whereas in case of this sample, ductile sample, you can see after yielding large amount of plastic deformation has been seen. So area under the stress versus strain curve nothing but toughness. So toughness value for both the samples is considerably different. For ductile sample toughness is very high, whereas for brittle samples toughness value is very low. So fracture. The most common type of tensile fracture profile for ductile metals is that represented here in these 5 figures, where fracture is preceded by only a moderate amount of necking. The fracture process normally occurs in several stages. The first, after necking begins, means that is after point M. Small cavities or microvoids form in the interior of the cross section, that is shown in figure B. Next, as deformation continues, so these microvoids enlarge, comes together and to form an elliptical crack that can be seen in figure C. And this crack has long axis perpendicular to the stress direction. So the crack continues to grow in a direction parallel to its major axis by this microvoid, and this process is shown in this particular figure. You can see the crack is continuously growing. So finally fracture occurs by rapid propagation of crack around the outer perimeter of the neck. So by shear deformation at an angle of about 45 degree with the tensile axis. So this is the angle at which shear stress is maximum. So sometimes a fracture having its characteristic surface contour is termed as cup cone fracture, because one of the matting surfaces is in the form of cup and the other like a cone. So this can be shown here, cup cone fracture. So cup cone fracture is the indication of a ductile fracture, whereas so this figure B is nothing but brittle type fracture, completely flat fracture, there is no deformation at all. So cup cone fracture is the indication of a ductile fracture, and how cup cone fracture occurs, that is evidenced here in these 5 figures. So this is the summary of today's topic. The phenomena of yielding occurs at the onset of plastic or permanent deformation. Yield strength is indicative of the stress at which plastic deformation begins. For most materials, yield strength is determined from a stress strain plot using the 0.2 percentage or 0.002 strain offset technique. So tensile strength is taken as the stress level at the maximum point on the engineering stress strain curve. It represents the maximum tensile strength that may be sustained by some specimen. For most metallic materials, at the maxima on their stress strain curves, a small constriction or neck begins to form at some point on the deforming specimen. All subsequent deformation ensues by the narrowing of this neck region, at which point fracture ultimately occurs, that is cup cone fracture. And ductility is a measure of the degree to which material will plastically deform by the time fracture occurs. So based on the today's session, one of the homework topic for you is what is mean by blue brittleness in case of plain carbon steel. So it is a very important topic, the blue brittleness in case of plain carbon steels. In forming industries, so blue brittleness phenomena is very dangerous and that has to be avoided. And second is the one of the numerical which is given to you. So solve this exercise. Thank you.